Hi, I'm Dr. Eva Horvath, and this is part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to derive Poisson's equation, Laplace's equation. We'll discuss boundary conditions, and we'll also discuss the behavior of the electric field in and around conductors. Last time around, we deduced two expressions. The first of which relates the electric field to the potential. The electric field is equal to minus the gradient of the potential. Gradient, as you'll recall, gives you the maximum rate of change. It gives you both the magnitude and direction of the maximum change. We also derived the differential form of Gauss's law, which tells you the divergence of the electric field is equal to the charge density divided by epsilon naught. I can substitute the first equation into the second. Giving me Poisson's equation. If we don't happen to have any charge in the direct area where we're solving this problem, the right-hand side of this expression vanishes. In which case, I have Laplace's equation. In the coming weeks, we'll be spending a lot of time solving this equation. There are two main techniques. One is called the method of images, and the second is called the separation of variables. As a reminder, this Laplace's equation written out in Cartesian coordinates is equal to the second partial derivative of v with respect to x plus the second partial derivative of v with respect to y plus the second partial derivative of v with respect to z equals 0. We'll be looking at problems that can be handled not only with the Cartesian form of Laplace's equation, but we'll also be looking at systems that exhibit spherical symmetry and also cylindrical symmetry as well. We'll also be discussing the uniqueness theorem, which tells you that if you find an expression that satisfies Laplace's equation, and that expression has the proper potential on the boundaries, or whatever boundary conditions you specified, then you are guaranteed that that is the correct solution. So I'm going to discuss boundary conditions next. We're going to derive a couple of them relating basically coming up with a relation to between the electric field above and below, or on opposite sides of the interface, if you will. Let's take our interface to look something like this. Just an irregularly shaped surface. And if I want to figure out what is E above and E below, how can I answer that question? Well, we might have surface charge density across the center face. Maybe we don't. Let's use Gauss's law. Gauss's law expressed in integral form tells you you've got your surface area, surface integral of the electric field is equal to the flux, so it's the amount of charge enclosed within that surface divided by epsilon naught. When we were doing Gauss's law problems, one of the first steps was to figure out what surface do you choose. If you were investigating the electric field of sphere, the logical choice there was choose another sphere. So if we were looking for the electric field inside, we choose a sphere whose radius was smaller than the dimensions of the object. If we wanted to choose, figure out what the electric field was outside, you choose a radius of a sphere that was larger. And from that, we could figure out what form the electric field has. When we were investigating cylinders, very long cylinders, very long wires, the sensible choice there was a cylindrically shaped Gaussian surface. When we discussed the electric field of an infinite charge sheet, the choice we made was the pillbox. And that's what I'm going to use to investigate the relation between the electric field above and below this particular surface. My pillbox is going to straddle this interface. I'm going to make it have thickness epsilon. And I'm going to shrink that epsilon. I'm going to take the limit as it goes to 0. Okay? When I do that, I'm not going to get any contribution from the sides of the pillbox. The only thing that's going to contribute is the part of the electric field, normal part that's pointing up, and the normal part that's pointing down. When we were looking at the charge sheets, we knew that the charge was distributed uniformly. I'm not going to make that assumption there in this case. I'm going to assume that I might have some kind of a odd distribution. So in order to handle that, what I'm going to do is I'm going to make the area of this pillbox very, very small. If I make it over a small enough area, over that very small area, I can assume that the density, surface charge density, does remain uniform. With that in mind, I can pick out the two parts of the electric field. In other words, the part that's pointing up here and the one that's pointing down over here. I'm going to take my normal and up in the upwards direction in both cases. So therefore, Gauss's law becomes the normal component of the electric field above minus the normal component of the electric field below has to be equal to, you should see that's times the area. That has to be equal to sigma area over epsilon naught. The areas cancel out, leaving me with the normal component above minus the normal component below equals sigma over epsilon naught. And N here represents the normal. I'm going to apply this boundary condition to some of the problems that we've worked through. We looked at the conducting shell that bore charge sigma, and we also looked at the electric field due to a uniformly charged sphere. This is my conducting shell. Inside, the electric field vanished. Outside, the electric field went as Q over 4 pi epsilon naught r squared. Again, it looks as if all the charge were concentrated at the center of the sphere when you're on the outside. I'm going to plug these two into the left-hand side of my boundary condition. So above, we have Q over 4 pi epsilon naught big R squared. Why large R? Because we're taking it right at the surface, right at this interface. And our sphere has radius R. Just inside, below the surface, the electric field vanishes. If I recall that sigma is equal to Q over 4 pi big R squared, I wind up with sigma over epsilon naught. So I can see that indeed for this particular example, my boundary condition holds, as it must hold for every system in electrostatics. The other example that we looked at was for a uniformly charged sphere. Inside, the electric field is equal to QR in the R direction, radial direction, over 4 pi epsilon naught big R cubed. Just outside, or actually outside, the electric field was equal to Q over 4 pi epsilon naught R squared in the radial direction. Once again, for a uniformly charged sphere, it looks as if all the charge were concentrated at the center. I'm going to plug these two expressions for my electric field into the boundary condition. First term is just going to be Q over 4 pi epsilon naught big R squared. Big R because we're evaluating it just above the surface. My second term gives me Q over 4 pi epsilon naught big R over big R cubed, which gives me 1 over big R squared, and that vanishes. So for a uniformly charged sphere, I have no discontinuity in the electric field. Why? Because there's no surface charge density here. Okay, so that's the normal component. What about the tangential component of the electric field? Sketch in a surface once again. Could be irregularly shaped, I don't know, it doesn't really matter. I have to use a different expression to investigate the tangential behavior of the electric field. I'm not going to use Gauss's law. I am going to use the fact that the line integral of an electric field around a closed path must vanish. So the path I'm going to take is going to be a rectangle, and it's going to straddle this region from above and below. I'm going to make the thickness of this path so small that the sides will vanish. The contributions from the sides will vanish. That will just leave me with a contribution from above and from below. In this case, we're going to look at the tangential component, and we see that it's continuous. Whereas with the normal component, you might see a discontinuity in the electric field. As far as the tangential component goes, that's going to be continuous. It's nice if you express these two equations in one equation in a nice compact form. So I'm going to write both of these together as the electric field above minus the electric field below is equal to sigma over epsilon naught. The components of each of these vectors are comprised of a tangential component and of a normal component. if I look at this expression here, and from the two problems over on the other side of the board, there is no tangential component to the electric field. So therefore, both sides are going to be 0, and this is satisfied immediately. And that's how the electric field behaves in a presence of an interface. I want to look now at what happens to the potential. Is there going to be a discontinuity there, or is it going to be continuous? You can make use of the fact of what the electric field is in terms of the potential. It's just equal to minus the gradient. So let's substitute this into that expression. In particular, I want to see what happens to the normal component of the gradient. So the normal component of the gradient is just the partial of v above with respect to n. Likewise for v below. What does n represent here? Well, it depends on what kind of system or problem that you're looking at. Let's say that you're looking at a disk, a plane, whatever. And let's say that this disk or whatever lies in the xy plane. And the normal to that surface is going to be in the z direction. And n here is going to be z. If you happen to be dealing with a sphere, the normal to the surface of a sphere is in the radial direction, and hence n is equal to r in this case. For the side of a cylinder, your electric field is going to be pointing straight out from that. In that case, n is equal to s. So because of the relation between the potential and the electric field, there's also potentially going to be a gradient, or rather a discontinuity in the gradient of the potential. Now, what about the potential itself? How does that go from above to below? I'm going to once again use the integral form of the relation between the potential and the electric field. And I'm going to evaluate this integral instead of from some arbitrary order of reference. I'm going to go from above and below. I'm going to look at what happens as I go from one side over to the other. If I take this little line element to be very, very small, vanishingly small as a matter of fact, what happens is that the right-hand side of this expression is going to vanish. It's going to go to 0. And what that tells me is that my potential is continuous. So the potential is continuous. However, the normal component of the gradient is, generally speaking, discontinuous. So it's once again useful to look at a few of the problems that we've solved already and see if these, or particularly that one holds. We've already looked at the electric field, which is basically where this one comes from. But if we look at the potential itself for our charged conducting sphere, inside we have Q over 4 pi epsilon naught big R. Outside, that's Q over 4 pi epsilon naught little r. But if we take this at the surface of the sphere just above it, so in other words, we evaluated R equals R, these two expressions are equal, therefore we see in this case this is indeed continuous across the surface. Now for the uniformly charged solid sphere, outside it's again, you're just going to have Q over 4 pi epsilon naught big R, or little r I should say. Evaluated the surface, we replace that with the radius of our sphere. On the inside, evaluated at little r equals to big R. I'll wind up with 3r squared minus r squared, and that once again gives me Q over 4 pi epsilon naught big R, evaluated at the surface of the sphere. So the potential is continuous, the electric field is not. We evaluate Laplace's, or solve Laplace's equation for a variety of systems. We're going to be using these along with Laplace's equation itself to determine solutions. Let's look at conductors now. Well, in our little world, we have conductors, we have insulators. In conductors, there are electrons that are free to roam. In insulators, on the other hand, the electrons are tightly bound to atoms or molecules, so they're not going to roam around. When we looked at the electric field inside of my charged conducting sphere, that vanished. And if you're thinking about this, you might say, well, gosh, it vanished. I can kind of see that intuitively because I've got all this charge uniformly distributed on the surface of it. So all those effects of those contributions to the field cancel each other out in the interior region. You might think, well, what if you have an oddly shaped conductor? Is that still going to hold? And the answer is it does indeed. So the electric field vanishes inside of any conductor in statics. And how can this be? Well, if you think about it, well, what if you have some charge free to roam around? It's roaming around in the interior. Well, electric field's not going to be zero anymore. It's not going to be statics anymore, is it? So the electric field has to be zero. But what if we stick our conductor inside of or into an external electric field? The electric field is going to the right. Is the electric field necessarily zero there? And the answer is yes. What happens is you'll see charge induced on the left and the right hand sides here, and that will give rise to another electric field. But this electric field counteracts with this one with the net result that E equals zero on the inside. So inside of any conductor in statics, the electric field must vanish. Now you might argue and say, well, it can't be static the whole time because the charge has to reorient itself, right? Well, the answer is that happens on a very, very fast time scale. So it reorients itself very quickly, and then the field will vanish on the inside. As a consequence of this, there can't be any charge on the interior of a conductor. So there's no charge inside a conductor. So in the interior, rho is equal to zero. So where, if you've got excess charge, must it be? It has to be on the surface, because that's the only place it can possibly be. What else can we deduce about the nature of conductors? Well, the surface has to be an equal potential. And looking at this expression here, if the surface of our conductor is an equal potential, that means the electric field has to be normal to the surface. Now, just think about this for a minute. What if you had a tangential component to the electric field in the conducting surface? If you have a tangential component to the electric field, there's going to be charges flowing. So therefore, the only way the electric field can point is straight up or straight out. This is our conductor. E is equal to zero on the inside. And the electric field points in the normal direction. And in accordance with our boundary conditions, there's a discontinuity in the electric field. It vanishes inside, just outside, it's pointing out, and it's pointing in a normal direction. Let's look at another conductor. I'm going to hollow out a cavity in this conductor, but this time I'm going to put a charge Q on the inside. Clearly in the cavity itself, the electric field cannot vanish. Why? Because you've got charge here, you've got flux. But yet, on the other hand, we've reasoned that the electric field must vanish inside the conducting material. So how do we handle this? What happens? How can this be zero when you've got Q inside? Well, what happens is that there's going to be charge induced of the opposite sign on the surface of the cavity. So this is a positive charge here. We're going to have negative charges. Induced. And those negative charges are going to be oriented such that the electric field vanishes outside in the conducting material itself. And you might protest, well, wait a second. We've got charge Q here. We've got charge of the opposite sign induced in some way on the surface of this cavity. But what happens? I mean, it just seems like we should have conservation of charge, should we not? Well, what happens is you'll see charge appearing on the outside of the conductor. Total charge in the conductor itself is still going to be zero, but charge or the electric field in the cavity is non-zero. Inside the conducting material, it's zero. Outside, the outside world's going to know that there is some charge Q, right? Because of the induced charge that appears on the surface, but it's not going to know exactly the nature of it. In other words, we're not going to be able to tell where this is in particular, only that there is some charge inside or of this system. On the other hand, if I were to bring a charge Q from the outside over here, this charge obviously has a field, or gives rise to a field, and this field's going to influence the outside of the conductor. It's going to cause redistribution of charge on the surface of the conductor, right? But it's always going to be such that the electric field inside the conducting material itself vanishes, okay? So let me state that again, or restate that. If I've got a charge Q that I stick inside the cavity, this conductor does not shield the outside world about information of Q. I mean, we don't know everything, we just know that there's some charge. On the other hand, if you bring a charge Q over here, this conductor will shield the interior from the field of this charge Q, okay? As I mentioned, in the coming weeks, we will be discussing Laplace's equation and applying those boundary conditions. For the next time around, we'll be studying work and energy, and we'll study how to calculate the energy, potential energy associated with a series of charges or a system of charges, and also with a system of conductors as well. And we'll see that there's some certain subtleties in how you define the energy of systems. That concludes today's lecture, and I will join you next time.